So let's review what we have studied so far. So far, we already discussed about grain size reduction, and we also already discussed about solid solution alloying. So in this video, we will talk about strain hardening, or also known as cold working. I hope that all of you already understand what are the concepts behind the strengthening mechanism so far. So strengthening can be defined as the ability of metal to deform depends on the ability of a dislocation to move. And by restricting dislocation motion, it can make the material stronger. If you still remember what we have learned previously, if we limit the movement of a dislocation, then we can reduce the ductility of the material, and at the same time, we increase the strength of the material. So other than grain size reduction, we already discussed about grain size reduction. We also have a solid solution alloying. There are two other techniques that we will discuss later. But in this video, we will talk about strain hardening, or also known as a cold working. And of course, we'll talk about precipitation hardening in upcoming video. As we already know, dislocation will disrupt the perfection of a crystal structure. However, if we make the dislocation nearer to each other, or in other way, in other words, we say that we increase the dislocation, then it will cause the motion of a dislocation to be restricted. And remember that when we decrease or inhibit the dislocation movement, it will make the materials stronger. So this is what we call as a strain hardening, one of the mechanisms that we use to increase the strength of material. So we can define a strain hardening as a phenomenon at which the ductile metal becomes harder as it is plastically deformed. It is often utilized commercially to enhance the mechanical properties of metal during the manufacturing or fabrication of material, and the effect of strain hardening can be removed by annealing treatment. Annealing treatment is when we apply heat treatment to the metal to remove the effect of a cold working on that material. Some examples of a material that can be cold worked are, for example, we can perform cold working on pure copper and aluminium to strengthen it significantly. So by applying a stress that exceeds the original yield strength of the metallic material, we have strain hardened or cold work the metallic material, and while simultaneously deforming it. And this is the concept behind many manufacturing process, like what we can see in the figure here. We have, for example, we have a forging, we have a rolling, we have drawing, and we have an extrusion. So let's take a look at the forging process. Forging process deform the metal into the cavity, a die cavity, and this will produce a relatively complex shape, such as an automotive crankshaft or connecting rod. Then we have a rolling process, and here we have we use roller to reduce the thickness of the material. And this process can be used to produce a metal plate, a sheet, or foil. Then we have a drawing. We have a drawing process. Here you can see that the metallic rod is pulled through the die, and this is done by forcing the work. This is what we call as work or metallic rod. We force it through a mold or die of a smaller cross-section area than the metallic rod. And the process is very quite similar to a metal extrusion, except that the difference being in the application of force. And then we have an extrusion, and here we can see that the material is pushed through a die to form a product of a uniform cross-section, such as a rod, a tube, or aluminium trim for door or windows to produce a wire or fiber. And other than these four processes, we also have other techniques such as a stamping method. A stamping method is a manufacturing process that we use to convert a flat metal sheet into a specific shape. So here we have the effect of a cold working on metal on brass. Brass is an alloy of a copper and zinc. Metal is said to be cold work if it is mechanically processed below the recrystallization temperature of the metal. And most of cold working processes are performed at room temperature. And hot working usually results in the refinement of a grain structure. And on the other hand, cold working will only distort or affect the grain and does little to it towards reducing its size. So here we can see that the effect of a cold working on the yield strength, tensile strength, and ductility of brass. You can see that in terms of yield strength, for 1040 steel for brass copper, we can see that the yield strength increase when the percentage of cold working increase, and the same thing happen for tensile strength. If we increase the percentage of cold working, the tensile strength also increase. And like what we expect, the ductility of the material decrease when we increase the percentage of cold working. And this is due to the limitation of movement of dislocation within that material. And as a result, the dislocation of that material will decrease. By controlling the amount of plastic deformation, we can control strain hardening. And we normally measure the amount of deformation by this equation. So this is the equation that we can use to measure the percentage of cold working. Here we have A naught. A naught is the original area of a cross section that experience deformation. And AD is the area after the deformation. So to determine the percentage of cold working, we have to minus AD from the original area of deformation, and divided by the original area of cross section that experience deformation. And by that, we can obtain the percentage of cold working. During deformation, the grain will rotate as well as elongate, and this will cause a certain crystallographic direction and plane to become aligned with the direction that we apply stress. And as a result, preferred orientation or textures will develop and cause anisotrophic behavior. And some examples of an anisotrophic behavior are fiber textures, sheet textures, drawing, and texture strengthening. In a process such as a wire drawing and extrusion, a fiber texture is produced. A fiber texture is a preferred orientation of grain that obtained during the wire drawing process, and the term fiber here refers to grain. And in sheet texture, the property of roll plate depend on the direction that we apply the measurement. For example, we can see here the strength of a plate here differs at the various position of the tensile bar from where the tensile bar specimen were obtained in this plate. And the strengthening that occurs by development of anisotrophy or of a texture is known as a texture strengthening. And some metals, such as a hexagonal close-packed metals such as magnesium, they have quite a limited number of slip system and brittle at room temperature. And because of that, only a small degree of cold working can be accomplished. If you want to know more about anisotrophic behavior, you can read more on this matter in the book titled The Science and Engineering of Materials by Donald Escalante on page 301. And here are some examples of fibrous grain structure of a low carbon steel that produced by cold working. We can see here that during a plastic deformation, using a cold or hot working microstructure that consists of a grain that elongated in the direction of applied stress is often produced. And here we can see that the change in the grain structure from a 10% cold working up to a 90% cold working. And we can see that from here, from 10% to 90%, the grains are severely elongated in the direction of the applied stress. And we can see at 90%, we can barely see the grain anymore because the grain has become too elongated. So here we have some disadvantages of cold working. First one is only a small size component can be cold worked easily. Only a small size component can be easily cold worked as greater forces are required for a large section, and typically sections of more than 25 millimeter in diameter rarely could be rolled, and due to a large deforming forces, heavy and expensive capital equipment. And here we have some examples of metals which can be suitably cold worked in the form of sheet or other form. For example, mild steel of a low carbon content can be suitable for cold working. And we have a copper and its alloy, including brass and bronze. Then we have aluminum bronze having aluminum less than 7%. And we have a nickel brasses. We have a monel metal. Monel is a nickel copper alloy. And stainless steel is also suitable for cold working. And we also have duralumin and several other aluminum alloy. Duralumin is a hard, a light alloy of aluminum with copper and other element. And here we can see in the figure we have an example of a dislocation during a cold work for a titanium alloy. And here we can see the dark line. The dark line here all represents dislocation line. And here we can see that the dislocation line entangle or one another during the cold work, and dislocation motion becomes more difficult, and as a result the material become harder and less ductile. Here we have an example problem on how to determine the percentage of cold working. So the question says that we have 1 centimeter thick copper plate that is cold reduced to 0.5 centimeter and later further reduced to 0.16. So we need to determine the total percent cold working and the tensile strength of 0.16 centimeter plate. So here note that because of the width of the plate does not change during the rolling, the cold work can be expressed by the percentage of reduction in the thickness T. So we can write down the percentage of cold working as the original thickness minus the final thickness divided by the original thickness times 100. And the original thickness of the copper plate is 1 centimeter, and the question says that the copper plate is reduced to 0.16. So here 1 centimeter minus 0.16 centimeter divided by the original thickness, that is 1 centimeter times 100. So we will obtain the percentage of cold working will be equivalent to 84%. So now we need to determine the tensile strength based on this graph here, the graph of strength in PSI versus the percent of cold working. So we already know that the percentage of cold working equals to 84%. So from the graph here, we can determine the tensile strength of the 0.16 centimeter plate. So from the graph here, since we know that the percentage of cold working is 84%, somewhere around here, and at the intersection here, so now we already know from the graph here the strength is approximately around 85,000 psi. So from the figure, we know that the tensile strength is approximately 85,000 psi if we cold work the material up to 84%. As a result of a cold working, dislocation density will increase. As we can see here, dislocation density increased for example, for a carefully prepared sample, the density can be around 10 to the power of 3 millimeter per millimeter cube. But for a heavily deformed specimen, the dislocation density could be increased at least 3 times to 10 to the power of 10 millimeter per millimeter cube. And here we have, from the figure here, we can see that we have two methods of dislocation density. The dislocation density is a measure of the number of dislocation in a unit volume of a crystalline material. And there are two methods that we can apply to measure this parameter. In the first figure here, we can see that the dislocation density is measured by the length of a dislocation, by the length of a dislocation line in a unit volume, and divided by the volume to give the dislocation density. And here in the second method, we determine the dislocation density by measuring the line crossing the unit area in the sample. So here we measure the dislocation line crossing a unit area in the sample. And this method, before that, N is a dislocation pit that can be revealed by etching, and A is the area, so the dislocation density can be determined by the number of dislocation pit divided by the area. And this second method is frequently easier to apply with a dislocation that are revealed by a chemical etching. And from the figure here, we can see that cold working generally result in higher yield strength as a result of an increased number of dislocation density, and the whole patch effect of the subgrain, and decrease in ductility. And now we will talk about 3 stages of annealing. We know that the cold working is an effective tool for shaping materials using a wire drawing, rolling, and many more. But sometimes this can lead to an undesirable effect, such as loss of ductility and development of residual stress. The 3 stages of annealing process that proceed as the temperature of the material increase recovery, recrystallization, and grain growth. Okay, before that, we know the properties and the structure that occur during the cold working. It can revert back to a pre-cold work by appropriate heat treatment that we call as an annealing. And like what I have mentioned before, there are three stages of annealing. We have recovery and recrystallization, and we have a grain growth. And here the effect of the cold work nullified. And remember that by heating the material or the specimen, uh, annealing will take place, and it can reduce dislocation density and will increase the grain size. And as a result, ductility will be improved, but at the same time, the strength of the material will decrease. So here we have a figure that shows the effect of a cold working and the effect of annealing. And here we can see that, as we already know, when we perform a cold working on material, for example, on metal, the tensile strength will increase, but at the same time, elongation strength will decrease. But when we do annealing or we perform a heat treatment on that same particular material, at a certain temperature, the tensile strength will decrease, but at the same time, ductility will improve. And here we can see other properties such as a grain size will pretty much same, up to 100% cold work. But when we perform annealing, we can see the grain size suddenly decrease and slowly increase at a certain temperature up to a maximum. And we can see the electrical conductivity is pretty much the same throughout both process. And the aims of annealing is one to increase ductility, we want to reduce hardness, improve the formability of that material, and we want to recrystallize metal, remove the internal stress, increase toughness. And we want to decrease the brittleness, and we want to increase the machinability of the material. And also we can uh, change other properties such as we can by annealing we can also decrease the electrical resistance and also improve the magnetic properties. So when we do cold work, tensile strength, like what I have mentioned before, will decrease, but ductility will decrease as a result of dislocation, movement restricted, grain size pretty much maintained throughout the process. But when we do annealing, the tensile strength decrease, the ductility improve, and we can see there is an abrupt change in the grain size, and at a certain temperature, the grain size slowly increased up to a maximum. A heat treatment can be used to remove the effect of strength hardening, and three things that can occur during a heat treatment, and three stages that heat treatment can be used to remove the effect of strength hardening, and three stages that occur during the heat treatment are recovery, recrystallization, and a grain And this is how we can differentiate between a cold working, a warm working, and hot working. TA here means ambient temperature, or we can say a room temperature, and TM is melting temperature. For cold working, the range is between ambient temperature up to 0.3 melting temperature, and for a warm working, the range is between 0.3 times melting temperature up to 0.5 melting temperature, and for hot working is within 0.5 up to 0.7 to 0.75 melting temperature.